Okay, so up here is a kind of a warm-up problem, the solve it they call it, that we're not going to go through completely, but there's a pattern here, okay? One kite has 5 ribbons. If you had 2 kites, you'd have twice as many ribbons, 10 ribbons. 3 kites, 15, 4 kites, 20. And you can use that pattern. You can make a table and then figure out how many kites you would need to have 275 ribbons. Now, this idea right here is that you can describe it in words. You can also use an equation, or you can use a graph to get that far up to find an answer. And it says sometimes the value of one quantity can be found if you know the value of the other. Like if you know how many kites, you could calculate how many ribbons because you know that it's a 1 to 5 kind of thing. And same thing here. If you know the number of ribbons, you can figure out how many kites. Okay? And another way of thinking about this is that if one number changes, the other changes as well. So you can represent the relationship between quantities in different ways: tables, graphs, equations. And just like before, we can tell if something's a solution to an equation by plugging it in. And it says you can use an equation with 2 variables now to represent a relationship between those 2 changing quantities. The number of kites and ribbons is not set. If you had more kites, you'd have more ribbons, etc. Okay? And we are going to now write ordered pairs. Ordered pairs are x comma y. Okay? And we're going to see how we use those. So here's the problem. Identifying solutions. If it's a 2-variable equation, is this a solution to this? Well, be careful, because the first value is x, the second value is y, and that's alphabetical. X comes before y in the alphabet, and x comes here first. Because in this equation, x is not first, but you need to know that 3 goes in where x is, and 10 goes in where y is. Is it a solution? When you plug it in, it actually doesn't work out to be a true statement. So no, 3 comma 10 is not a solution to this 2-variable equation. Okay? Your got it problem is to test out these ordered pairs by plugging this in for x and this in for y and seeing if you get true statements, and do it for each one. Good luck. Okay. Both Carrie and her sister Kim were born on October 25th, but Kim was born 2 years before Carrie. Kim is older. How can you represent the relationship between Carrie's age and Kim's age in different ways? Well, we have the 3 different ways we're going to do it. This is what we know. We need to represent it in different ways, and we're going to do it like this. So let's first make a table. Okay. We know that Kim was born 2 years before Carrie, so Kim is 3 when Carrie's 1. Okay. Carrie is 2 when Kim is 4. Since she was born before her, she's older. All the way through. That's the table. We're going to make an equation for it now. And what does the equation look like? Well, we're going to say, okay, if x is Carrie's age, and remember, Kim is older, so we're going to get Kim's age, we would say, okay, let's make that a different variable. That's y. And you can see that y, Kim's age, is always 2 more than Carrie's age. So if you take whatever age Carrie is, x, and you add 2 to it, you're going to find out what Kim's age is. Exactly. Okay? Now we're going to draw a graph for it. And here's what we say. We say, okay, when Carrie was 0, Kim was 2. When Carrie's 1, Kim is 3. When Carrie's 2, Kim is 4, etc. And you plot all the points all the way up. Does it make sense to connect them? Yeah, you hit every age between 0 and 1 and all the way along. Okay? So it makes sense to connect them. You'll find out later reasons why you might not be able to connect things, because you don't have values between certain numbers, but you're just only at those numbers. That's how you represent it. Here's your got it problem. Will runs 6 laps before Megan joins him on the track. So Will is always going to be 6 laps ahead of Megan if they're going to be at the same speed, because they run at the same pace. How can you represent the relationship between the number of laps Will runs and the number of laps Megan runs in the different ways? table, equation, and graph. That's one thing that you're going to do. Also, you're going to describe how the graph in problem 2 above would change if the difference was 5 years between them instead of 2 years. Try it out, see how you do, look at the answer when you think you've got as much of this answered as possible. Good luck. We are defining inductive reasoning just as the process of reaching a conclusion based on the pattern that we observe. And you can use this reasoning to predict values. We're going to do that now. Don't get too stuck on this. It's just the idea is saying we look at the patterns and we can say, based on what I see, I believe this is happening. And we can then make predictions. So now we are extending a pattern. We are saying the table shows the relationship between the number of blue tiles and the total number of tiles. For every total tiles 9 that you have here, one of them is blue. So if you then say we double that and we get that same pattern a second time, now we've got 2 blue tiles out of the 18 that are here. If we do it again, we got 3 out of 27, and we can extend this pattern to say 5 would be 45, etc. Okay? What do we want to do with this? What is the total number of tiles in the figure, in a figure with 8 blue tiles? So we could hopefully continue this table. That's one way to do it. We could also draw a graph where here's the graph, and you say here's the number of blue tiles, and here's the number of total tiles. And notice that these are going by 1 here, but these are going by 9. You can change the scale. Like this can go by 1 each time, and this can go by 9 each time. You can change the scale on the XY, but this has to stay. If you go 1 unit, 1 unit, 1 unit, 1 unit, it has to be consistent all the way across. And if here you go 9, 9, 9, 9, then everything's got to be a box that needs to be 9. Okay? And so then you can then say, I'm going to continue the line like that, and then find the point where you have 8 for the number of blue tiles, follow it up, and if you follow it over, then once you follow it up until you hit the line, follow it over and see what number corresponds for total tiles, right? What's another way? Oh, and by the way, can you connect those points? Not really, because you don't have values between 1 and 2. You either have 1 set or 2 sets, 1 blue tile or 2. You don't have 1.5 blue tiles, so it doesn't make sense to have a value at 1.5. We'll get to that again later. But that's an important thing, the difference between whether you connect it or not. Okay? What else can we do? Well, we can write an equation. We can say, if we take the total number of blue tiles and we multiply it by 9, we'll find the total number of tiles, because the number of tiles is 9 times the total number of blue tiles. So then you said, okay, what if you wanted 8 blue tiles? Well, x is the number of blue tiles, so you put in 8 for x, and you find out 72. Either way, the total number of tiles is 72. This is a got it problem. Use the tile figure from this, problem 3. Make a table showing the number of orange tiles and the total number of tiles. How many tiles in all will there be with 24 orange tiles? That's the first part. And then make a table showing the number of blue tiles and the number of yellow tiles, blue to yellow. How many yellow tiles will there be in a figure with 24 blue tiles? Good luck. This is getting into the real big stuff that we're going to be doing for this course. So I suggest you do the lesson check and see how well you understand this, and then ask me questions. Really good idea to do these right now. So try them out, then check your answers. Good luck.